and IETF is in 3 weeks.
Yeah, yeah.
Can you see my slides? Are they moving?
Yeah, they look good.
Cool. So I'm not
And
our screen. I'm not seeing you actually.
okay.
Or we can.
Okay. In the meantime, we're live here. So greetings, fellow nerds. Here we are with another life-changing episode of Between Two Nerds, where my friend and co-host Jeff Tansura and I talk about all aspects of the networking industry, from protocols old and new to industry trends and drivers to up-and-coming technologies, and really the topic of every episode, things you should know to further your career. Hi, Jeff.
Hi, Jeff. Great to see you as always.
Yeah. It's if I enjoy this. Oh, we've got the little mirror effect there.
Yeah, infinity effect.
The infinity effect. Yeah. That should go away in a minute, I believe. But anyway, yeah, it's just like the episode before last. We had Dino Farinacci on last week, which is or last episode, which was a great episode. I really hope we can have him back sometime. But the episode before that, we were talking about just revisiting BGP in the data center. And we really didn't get finished there. So we're just going to pick up where we left off. And for you viewers, Jeff and I both were actually before the show having to say, where did we leave off on this? And both of us were scratching our heads a bit, but we did finally figure out where that was. So anyway, Jeff, you want to? You've got some slides that
Sure.
that I believe is just a continuation of what you had before. You want to bring those up? Hey,
Okay.
look at
Well,
that.
this is a slide that was used last before we adjourned months ago. So we are going to restart here. Kind of some background. So the discussion started partially on Twitter, partially on LinkedIn about, why should I use BGP? Well, how is BGP different? Why isn't there SPF and this kind of stuff, right? So
yeah, I love this. I love this formula that you got on this slide. By the way, I would love to steal that sometime for the next time I update my own BGP book.
Sure. So probably it would make sense to go again through this slide, and then I would like to cover really failures and what BGP does, what it needs to do, and talk about some unique features of BGP, right?
Great.
So let's go back here. So what you see here is total convergence framework for BGP on leaf-spine network. So failure detection time is very important. As we said, it's very different depending how a vendor implements it. It could be done completely in hardware and potentially in microseconds. Could be done partially in hardware, partially in I mean, it's not software how in sense more firmware, but then we are talking about 1 to 10 milliseconds, right? Or it could be done naively. You would see it probably in like really software stacks, and then we are talking seconds, right? So failure detection time is fundamental for convergence to start. When you know there's a failure, you react on it.
So looking at what you've got it as an extreme case there of 180 seconds, would that be, for example, a router that's maybe behind a switch or something like that? That's
Something like that. So case when you cannot detect loss of signal or loss of light, and you don't run BFD. So most vendors have default timer for eBGP set to 60 seconds. Obviously changeable, but practically if you just deploy it out of the box, you'll end up with 3 keep alives of 60 seconds. So whole time is 180 seconds. So practically you'll see the situation mostly, again, if you are behind the switch. There are also some optical subsystems that don't propagate failures, right? So even if you lose light on one side, it's not going to be propagated to another side. So on the client interface, you'll see light. So obviously you will wait for BGP to time out. So you want to be fast here. The faster, the better.
Yeah. So worst case is triggered on loss of hellos.
Yeah, so there's also some nasty failures, like bugs in forwarding, for example. So imagine situation when your port is still up, but your ASIC refuses to forward IP traffic. Uh, People who played with it know what I'm talking about. I'm not going to name the vendor. Practically, you might run out of credits for IP traffic. So
Mhm.
link is up, ASIC is kind of working, but not forwarding any IP traffic, right? So if you are relying on keep alive, again, worst case, you are down to your hold time, which could
Yeah.
be 180 seconds. So don't be that guy. So BFD is a great protocol, right? It's fast, it's
Yeah.
reliable, it's implemented in most cases completely in hardware. Uh, there are a number of points. So do use BFD. However, many people use logs in their network today. In some cases, it's not really because of resiliency. For example, you could see single link in a log, right? So you don't gain any resilience. What you do gain is if in the future you want to add additional link or additional four links, you don't need to change anything on NP layer, right? So you kind of abstract their single IP endpoint. Uh, the problem with the BFD over LUC is a separate protocol. There's an RFC for it, and it needs to be implemented. For example, FRR and Sonic still have no implementation for that, right? So you cannot really run BFD over LUC. In this case, you need to execute each constituent of the LUC, and then it's subject to mean link, and so you need to follow LUC semantics, in other words, right? So if
Right.
you use LUCs, you might be out of luck, especially if you're using FRR.
Hmm.
Uh, okay, so be quick here. Fast rehash. Probably I shouldn't be repeating everything we discussed. Make sure it's properly supported on your vendor. Make sure that if you have some timers that kind of wait before notifying upper layer to react on it. So we discussed there's a vendor that has 100 millisecond default. And again, we are not judging whether good or bad. It's just there and for particular reasons. You
Yeah.
really want to hide flapping links, right? You don't want every time your whole routing machinery to kick in if your link goes up and down.
Yeah.
Practically, you are waiting. Your converge time is longer.
Yeah. And that's, I mean, in a lot of cases where you have adjustable timers for any protocol, I mean, that's something that a lot of people seem to miss is that, you don't necessarily get better reliability simply by reducing timer periods. There's always a price to pay for that.
Yeah. Uh, so BGP to RIP installation pretty fast today. So last measurements we did on FRR, we were able to get 1 million route down to RIP in 7 seconds. So which brings us really to what 170K routes per second. So down from BGP RIP into RIP. So as we said, the bottleneck today is FIP. There's a lot of work being done, for example, in Sonic to increase this number because there's a lot of inefficiencies in the way route being installed and already synced, but it's completely separate discussion. And then peer updates. Uh,
Sorry, you said inefficiencies in the fib, right?
Inefficiencies in I mean, those are artifacts of designing a system in subpub matter, right?
Yeah.
So if you look at Sonic, you've got Redis and then all the containers that provide this communication. But it's also in a way, right? So practically, if you look at, uh, let's call it carrier grade routers,
Hmm.
the route installation usually done through shared memory, it's very, very fast, right? So you're trying to spend minimum amount of time in between. You want to see routes that in your RIP, in your FIM as soon as possible. Because
Yeah.
the longer there's inconsistency, the longer it takes to converge. Moreover, since you are advertising your updated routes to your peers in parallel, you might create loops, right? Because if your RIP says one thing, your FIP says another thing,
Yeah.
there's definitely a possibility for a loop. right? So all important considerations, and convergence is not the one thing, it's combination of all of those. You might be amazing at failure detection, but if something else takes longer, you're still your weakest link. So make sure you understand the sequence of events, how they work, very important, how to troubleshoot them. And this is pretty much what it does to your conversions. So let's take a look at different failures in different modes. So as always, we keep our focus on data center. And in this case, we are using three-stage leaf-spine network. So 5 stages more complex, but
Yeah.
practically what you see on spine there is more or less replicated to super spine level. So we are looking at link failure, and the server is single humped in this case. So in other words, a server is connected to a single top of the rack switch. And we also have direction. So server to leaf is fatal. So if you lose the link, your server is not connected to the network anymore. Nothing you can do. So convergence actually doesn't really matter.
That's if you have a single top of rack leaf and no multi-home servers, right?
Yeah. So, and many networks are built this way, and the assumption is then that your application can survive this fatal failures. So if your application actually cannot survive it, probably you should consider dual homing, maybe another Tor or some other way,
Yeah.
which will again require probably 2 NICs on the server or more. So make sure that your infrastructure can support your applications. Because if it's not the case, then probably you need to invest. You invest either one or another. I mean, there's no free lunch.
Yeah.
So local from leaf to spine, all destination is still available over all remoting spines. So you just lost a amount of bandwidth that is a fraction of number of spines here. So on leaf side, it needs to detect the failure as soon as possible. So here we're talking about fast rehash. So you want to stop sending link or traffic on the failed link as soon as possible. So you need to do fast rehash, move all the flows that have been mapped to the failed link to other links, right? This needs to be done in forwarding, not in control plane.
Right.
And eventually, after you've done this and you update your rip update BGP that next hop has disappeared, you update all the BGP peers, in this case spines, and eventually the sender Tor will not be sending traffic towards failed spine or spines that has no connectivity to the end destination. Right, so pretty simple case. Remotely, if you look at spine to leaf, you want the spine that is connected to fail link to text failure as soon as possible and update its peers.
Mm-hmm.
Right, so what it need to say, don't send traffic towards this particular server towards me. So there's 7 other spines that are connected to it. So the source Tor will just remove next hop towards particular destination and start using it. So this is where the GP convergence is involved, obviously, because it's remote. So dual home servers. In this case, I would use Anycast. So in other words, you are advertising same IP address or same reachability over both stores. So it's a bit more complicated. So let's go through the failures here.
Yeah.
So when Leaf or Tor detects the failures, the destinations or sources are still available over second Tor, right? So they're not becoming unreachable. What you need your network to know is that you should use only leaf that is still connected to the spine to which first leaf has failed, right? So BGP need to update all the spines. Spines will update all the senders in this case, not to send traffic to the leaf that failed. So what's important here Reachability is still there, however, you've got less bandwidth over it. So here in steady state, you have two links. So let's say they're 100 gigs. So you've got 200 gig of connectivity to our server. The server has dual NICs that connected to dual Tor. So now you've got less bandwidth. And we are going to use weighted CMP to signal to the source, to the sender, to hash traffic differently. And this is kind of next topic for discussion. So switch failures are similar. So if you lose leaf in single home scenario, the failure is fatal. You just lost all your servers connected to it. So really nothing you can do. In dual home case, again, you lost the leaf. So you lost half your capacity, but not the reachability. So two things need to happen. One is not to send traffic towards a failed switch. So you will locally detect there's a failure and do fast rehash on the spines that are connected to the failed leaf. From BGP perspective, you need to update your peers, and potentially you need to rebalance traffic, and that's the next topic. So traditionally, BGP is not bandwidth aware. Like it's using IS path length as the main characteristics of the path. The longer, the worse. So let's go through history. So link bandwidth draft stopped its development in 2016, got implemented in Cisco universe. It's known as DMZ community. Practically, it's a bandwidth of next hop and hot in the community. The initial draft defined it as non-transitive. In other words, you cannot send it to eBGP peer. And what's important, it's not changing the equal multipath selection logic, right? So it's exactly the same. It doesn't make BGP an equal load balancing. So this is common mistake. The cost is still, it must be equal for BGP to load share. What is changing is weight associated with particular path. So we'll go through more details, but this very common mistake, BGP doesn't become protocol that does unequal load sharing. It's still equal, weights are different, so you load share differently. Given all the, it was at the time designed for particular reasons, right? But looking at it today from a larger BGP network perspective in data center, those requirements don't work for data centers. So there's another draft that is very close to become RFC. We are working on it, and it's a bit complex because there's older draft. So the real question is, what do you do in your draft? You merge it with old one, which didn't work because the author's full draft didn't really respond to like 15 emails I sent them over the last 6 years. And another point, as we said, the extended community has been defined as non-transitive. So you can fix it in two ways. You can squat or make it transitive and configurable potentially. So it's up to you whether it's transitive or non-transitive. The problem with it, you really should follow IETF and IANA allocation. So if something's non-transitive, probably it should stay non-transitive. FRR implements it as transitive, but you can configure it being non-transitive. So it's really up to you how you use it. So let's take a look at how the requirements have changed. And there is a number of implementations of the cumulative bandwidth, which is kind of extension on top of base link bandwidth draft. So this is an original solution that is non-transitive. And since non-transitive, it can only be propagated to iBGP peers, which kind of makes it completely unusable in the eBGP in data center case. Right, so the initial idea was you propagate bandwidth to your iBGP mesh based on your eBGP peering interface speed. So it was only static and not only meaningful to nodes that are directly connected to it, right? If you have nodes that are 3 hops away, and getting a regional bandwidth is completely meaningless because your links are not necessarily of the same speed, right? And the distribution of links is not necessarily the same between different layers. So vendors started to tweak it in different ways. So first one was to kind of ignore non-transitivity and but still make it only usable for directly attached peer. Add pass didn't really help. There was one implementation, pretty much irrelevant. So anyway, all of this led to implementation of actually creation of the DMZ, the eBGP DMZ draft. It has number of hyperscale requirements. So at the time at Microsoft, I included some parts that potentially could be used there. So let's take a look how it works. What you see here is actually, let's use Letterpoint. So what you see here is 2 ports and 5-stage network, right?
Mm-hmm.
And reference bandwidth is 10 or 10 gig. In this case, it's easy to understand. So the advertisement of prefix left to right, traffic is sent right to left, as we always do. So we advertise prefix P from L11 to S11 and S21. We have 2 links between each switch to each spine. So here we multiply reference bandwidth by number of next hops. This is pretty much the math behind the feature. So when we receive it in S11, we advertise it further. It will have bandwidth cost of 20, which is 2 times 10 gig. Here, connectivity to super spines is segmented, which we often do to widen radix. So there's only 1 link from each spine to each super spine. So the multiplication is by number of next hops we set or links, which is 1. So 20 stays 20. As we go down to our second pod, now we've got, in this case, 3 links from each super spine to each spine. So we receive the prefix P over 3 different peerings. We multiplied, received weight by number of next hops, in this case 3. So our total is now 60. And then on receiving side, we receive it over 4 links. So we multiply 60 by 4, which gives us 240 in total. 240 divided by number of links results in ratio of 1/4 of each link. So what you are getting here is basically CMP, right? Because your network is completely symmetrical. So you could have achieved it without doing any of that because your network is symmetrical. Let's take a look at failure. So same network, but now prefix P is advertised to S11 over 1 link because 1 link went down, but to S21 over 2 links. So when we advertise it to our super spines that are connected to S11 receive prefix with weight of 10, while super spines that are connected to super spine 2 receive it with a cost of 20. So exactly the same number of links as we go down. However, now multiplication is different. So when we advertise it to second pod spine layer, spine that is connected to SS1 will receive a cost of 10 and multiplied by 3. So that was going to be 30. While S22 that's connected to SS2 will receive it with cost of 20. And by multiplying it by 3, you'll get a value of 60. So when we get to the sender or actually receiver of BGP updates, you will see that total bandwidth available through S12 is 60, while bandwidth available through S22 is 120. So as we start dividing across each link, we will be sending 33% to S22 and 16.5 to S12. So, which will result in less traffic arriving on S11 and more traffic arriving on S21. By doing so, we are pushing the congestion, if such can arise, to the source, which is much better than having it here and dropping traffic. Right? This is how BGP signal asymmetrical bandwidth in the fabric. The speed of propagation of this information is similar to any BGP update. So when there is a change, you'll generate new route, and then you will update the value in the community. What it also does, and it's important to understand, it defeats some of the BGP hiding. Because remember, as we discussed, BGP, if best path is not affected and reachability is still there, will suppress the update. So it will hide it. Here, since you need to update value in the wait community, it will actually need to generate an update. So you might see increase in number of updates. It's insignificant, but it's different and it's larger than if you don't use this feature. So why is this important? It could be used in two different directions. So what we see here is really from source to, or from destination to the source in leaf-spine network. If you take any cast scenario when you have number of servers connected to a Tor and you anycast, so you load balance, and it's very often done in data centers, right? What you could do now is to say, I can now change weight or cost of the route based on number of servers connected. All right, so you have 4, you advertise 40. You have 8, you advertise 80. So suddenly you can notify all the BGP speakers on the network that you can consume more traffic. So it's more application, or I mean, it's physical connectivity, but you are hinting your network that there's more capacity to process it.
Yep.
If you look at hyperscale network, very often, if not always, you're connected to external world, not through exit pod or exit rec, but through superspine levels, right? So your superspine would be connected to some kind of regional aggregation. So the amount of bandwidth in data center is abundant usually. And since most data center run below 50%, if you lose a link, so be it, right?
Yeah.
Amount of optics in the fiber or in the ground is significantly less, and very often it's bundled. So you've got bundle of 8 or 16 fibers, and if there's cut, it might potentially reduce your capacity not by 1/8, but actually half. Right? So it might be very important to signal that you've lost some capacity relatively far away from data center. So imagine somewhere above regional aggregation layer. So you would really like your data center send less traffic to the left and more traffic to the right, because usually you would see rings that go out of data center towards some kind of regional aggregation, right? So that's another very important use case. It's actually described in the draft.
Yeah.
Right? So if we look at IGPs, without extensions, none of them support this kind of functionality, right? Either SS or SPF, they provide the ability to do basic ECMP without understanding of bandwidth available. So in other words, if bandwidth somewhere else is less, you're not going to ECMP anymore because the path is not equal, it's lesser. We added extensions to IGPs to signal bandwidth in segment routing. So if you read segment routing RFCs, there's number, so almost in all TLVs that provide signaling between different nodes, there's wait part that can signal bandwidth available. So, but those are kind of exclusively used by segment routing. They are not in vanilla IGPs, and the feature is hence unique to BGP, and perhaps another reason to consider BGP if you need this kind of functionality. So again, based on the discussion we had with Ivan and more people, if you have network with 4 switches, you can provision static routes for,
Yeah.
8 switches, still you can run whatever you like. You like RIP will still work. You start thinking larger networks. You really need to start considering how you deal with asymmetrical topologies, especially if you run your network hot. Again, if you run your network 20% utilization, you don't really care. You'll survive failure. You'll probably survive double failures. If you run your network 70, 80%, and probably this is really where you want to be to utilize your investment wisely, on the failure, suddenly you might start dropping traffic, right? So you would really like to have ability to know how to load balance traffic more granularly, given you're using CMP, and again, outside of Google and few more companies, is probably what you're using anyway, right? So another point for considerations, whether you want to use BGP, whether you want to use something else, and kind of pros and cons of each solution. And I think I'll stop my presentation here. We are 11:30, and
Yeah. I believe you were saying you have a hard stop about 3/4 of the hour.
yeah, so I should have bad delivery, but no one knocked on my door yet. So
Well, unless we want an unexpected guest, it's probably best to. That is it's a fascinating. You can always tell when I get fascinated, whether it's you or a guest or whoever, getting into things that I find interesting, because suddenly I shut up and I'm just in listening mode, and this was certainly one of those times. And I have to say myself, I'm going to go back and review those drafts.
so
That was really informative, in my opinion.
thank you. I appreciate your, especially coming from you, right? So practically, people are implementing it. It's not theoretical discussion.
Yeah.
Right. So
is it being implemented? I mean, you gave your example mostly in a 5-stage CLO network. Is it widely implemented, or is it mostly hyperscalers, or even just larger networks, or is it pretty widely implemented?
And so weighted CMP specifically is well understood technology. It's been around for 7-8 years.
Yeah.
But now you can actually use in data center with all the changes. So what we didn't discuss is actually what draft does and what I think we should do in ATM. So the community is non-transitive.
Mm-hmm.
In order not to break the logic, most implementation, they re-originate. So transitivity means that you are actually just sending over. If it's non-transitive, you are not allowed to send it to your BGP peers. That's what kind of logic behind, right? So if you look at most implementations, what they did, they kind of terminated and re-originated, right? So it's kind of transitive, but it's not.
Yeah.
And that allows the draft to be informative because it doesn't change or informational, because it doesn't change any logic. Practically, I think, so this is where we are trying to get before draft progress into our RFC. I think this draft should become standard track. We should change community to transitive and just be an update.
Yeah.
I can imagine that original authors might disagree with it. So, but then they need to work with common set of authors. And I offered my volunteering to kind of be in between the people and actually bring it to successful completion. But so as of today, most implementation will regenerate on FRR. it's by default transitive. You can configure it as non-transitive. There's a CLI to do so. So this is where we are. And
all right. Cool. Well, I would have to pay attention to that at the next IETF.
yeah, so IETF is in 3 weeks. Exciting.
Yeah. In Prague.
Yep. So important point. Many of you don't know, but for the first time, we had a side meeting dedicated to routing in machine learning clusters. Probably a few hundred people attended. We had issues with Wi-Fi. Guess what? So, so half of presentation didn't get presented, and recording got lost.
Oh man.
So, but this ATF in Prague, we are going to prepare. Actually, we are going to get to the room. It's myself and Injing. So we are doing it in the routing working group context because it's routing, but specific for machine learning clusters. So we'll come hopefully 30 minutes before. We'll make sure WebEx is working. And anyway, so we are going to hold one in Prague. We are going to record it. We've got an exciting agenda. So we've got at least 2 hyperscalers talking about their work. We've got a person from a startup working on very different way of building networks and infrastructure in general. And I'll probably do some educational session on RDMA over IP, what Rocky is, how it's different, and very important topics if if you're interested how you can connect more than one GPU. And if you look at OpenAI, we are talking about 100,000 of those together, right?
Oh yeah, I definitely want to watch that session. I'm not going to be there in person, but I'll be there virtually this time. I really would have loved to just have a good excuse for going to Prague, but we've got a network automation forum event the following week that I'm busy with, so I decided probably shouldn't make myself jet lagged getting back, the evening before that event starts. So I'll just be there virtually this time.
I'll send you virtual chat beer.
Yeah. Okay, well, Jeff, thanks so much, and this was a shorter session, but hugely informative, and really appreciate your sharing your vast knowledge as usual. And sometimes it's fun, just the two of us here.
It is always fun with two.
Yeah. Okay, so we'll be back week after next. Don't know the topic yet. I've got some ideas. Jeff, I know you probably have some ideas. I'll be at Nanog, but at least on my part, I'll be transmitting from a hotel room somewhere instead of my ugly old office here. But we'll see everybody again in 2 weeks.
Bye, everyone. Bye, Jeff. Robert, thank you.